what is a power factor, how do we calculate it, what are its types, the reason behind power factor, and many more things. So let's go for a ride. Power factor is a term to measure how effectively incoming power can be used in our electrical system, and it is defined as the ratio of real power to apparent power. The real power is the power that actually is being provided to the equipment and it performs useful and productive work. It is also called as actual power, active power, or working power. The reactive power, on the other hand, is dummy power, or the power which cannot be used. And there comes the apparent power. It is the vector sum of real power and reactive power. This is the total power supplied to the power mains that is required to produce the necessary amount of real power for the load. There are two types of power factors. First is the distortion power factor, and second is the harmonics power factor. First, we'll look into the distortion power factor. The harmonic power factor is quite advanced and tricky to understand. This type of power factor occurs in the switch mode power supplies. To understand the power factor better, let's see a very simple example with my favorite analogy, which is the beer analogy. Let's consider the glass of beer. The glass represents the apparent power, which is supplied by the mains to an electronic appliance. Whenever we order beer in a glass, we get the beer, and along with that, there comes the foam. Well, if you are drinking the beer from bottle itself, this analogy is not for you. Now, the portion of your beer is represented by the real power. Unfortunately, this foam steals your enjoyment of having beer, and this is represented by the reactive power. The total content of your glass is made up of active power, that is beer, and reactive power, that is foam. You don't want the foam, but still it comes along with the beer. Let's compare this analogy with the power triangle. The true power is the adjacent line, so this is our beer. Then on the opposite side, there is the reactive power, which is foam. And the hypotenuse side is the apparent power. Let's consider this angle as theta, which is between adjacent side and hypotenuse. As we increase this angle, the reactive power and apparent power increases, keeping the active power constant. And the size of glass and foam is increasing, but the content of beer is the same. So according to basic trigonometry, the cos of angle theta can be given as the ratio of real power upon apparent power. So the power factor is also known as cos theta. We should have power factor very close to 1. So the angle theta should be towards 0. Then only we get the value for money which you are paying. That is full glass of beer without foam. So even if we are using just the active power, we actually have to pay the cost of total apparent power. For example, there is an electronic appliance which consumes the power around 100 watts and its power supply has 80% of power factor. Then it actually consumes around 125 watts of power. So 25 watts is the excessive power which we will be paying for. Well, what causes the distortion power factor? In electrical terms, there are basically three types of loads. First is the resistive load, then capacitive load, and inductive load. Well, a combination of the different loads can be also chosen, but we'll not see that right now. If we connect the purely resistive load to an AC power mains, the voltage drop across the resistor and current flowing through it are always in the phase. So the power factor of the system is 1. there is no reactive power in this. If you draw the phasor diagram of this system, both voltage and current are in the same direction. Second is the purely capacitive load. In this case, the current and voltage are out of phase. The voltage starts from origin, but the current starts from the peak value, which is why it can also be said that the current is leading over voltage, so it produces the leading power factor. If you multiply the current and voltage at any instance, we never get the maximum power out of it, even if the proper input is provided. So the power gets wasted, which is reactive power. There are not many types of capacity loads out there, so we'll jump on the purely inductive loads. Here the voltage starts from the origin, but the current starts from the negative peak. So the current is lagging in this type of load. If we draw the phasor diagram of the inductive load, it will look like this. So this type of power factor is known as lagging power factor. And guess what? All the induction motors and transformers which we are using in the industries are inductive loads. And these machines are widely used in the factories. So maintaining a good power factor is a very big challenge for them. Just like we have to pay for the foam as well in the glass of beer, we have to pay the price of reactive power, even if it is not being used. So, to get the good power factor, they use big capacitor banks to compensate the phase of current. So, if the inductor has a lagging current, they use certain value of capacitors which will bring back the phase of the current to origin to get the power factor close to 1 or unity. So there is a tug of war between capacitor and inductor about getting the current on the right track. Well, that's the industry level of power factor correction. There is one more type of power factor, which is the harmonics power factor. It occurs in the power supplies which are situated in our electronic appliances. In power supply, no matter if it is a linear power supply or switch mode power supply, there is a bridge rectifier at the input which rectifies the AC sine wave, and there is a capacitor connected after the bridge rectifier which filter out the AC components. This big capacitor gives the DC voltage to the DC to DC converter, and this DC to DC converter steps up or down this voltage according to the output requirement. Well, the voltage gets rectified. The waveform of the input voltage and current looks like this. If you check the current, it flows to the capacitor only when the input voltage reaches to its peak value. The capacitor charges quickly during this time and it discharges slowly into the output side. If you notice, the current and voltage are in the same phase. But the current flowing through this is not linear. Sometimes it flows, sometimes it doesn't. And this is known as the total harmonic distortion. The distortion means that there is a change in the original signal. Here you can see the change in the current. A perfect sine wave has no harmonic components. That means if the input is given as the sine wave, and if we are not getting the component of perfect sine wave out of it, then we can say it has harmonics. If we check the fast Fourier transform of this current in the oscilloscope, it has a high peak or a bar at start, which is known as the fundamental frequency. And these small bars are its harmonics. These harmonic distortion should be as minimum as possible because these high frequency current components have various undesirable effects on the electrical systems like core losses in the motors, or it causes electromagnetic interference with other electronic systems. Due to this, the power factor of the system decreases as well. Let's summarize this in easier terms. The power factor of the system is nothing but the ratio of real power and apparent power. The real power for our system will be the product of sinusoidal RMS voltage and its peak current. So it will be first harmonic of the voltage and current multiplied with the cos of theta if there is a phase shift between current and voltage. And the apparent power will be the total power, which is RMS input voltage and ideal current without this capacitive load. If you compare these two waveforms, the power factor of the system will be less than 0.4 or 0.5. Now check this beer glass. Considering only 30% of the beer and 70% of foam. Still you are paying for the whole glass. That's not fair, right? Well, there are different power factor correction methods to look after this harmonic power factor, and that part we'll see next time. So that's it about the power factor. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to my channel, and finally, thanks for watching.